So we have run big data projects for both NASA as well as for the medical school. On the medical school side, and that was our first attempt at sort of a big data problem. And if you think about it, the Wikipedia question was also a big data problem as well. There, we were interested. What's happening in medicine and genomics is that there's an explosion of data gathering. So now they're doing these massive studies, genome-wide studies, where they're getting basically terabytes of data, of genomic data. And
so basically, genome processing is following the standard technology curve.
Exactly, Moore's
Every
law.
year
Exactly,
you're doubling the amount of genetic data you can capture.
Exactly, and then you have
the
to
speed they can capture.
Exactly, and then the question becomes, how do you analyze all this data and how do you make sense of it? So we had a colleague. Some of my work is with the medical school, where they have an initiative called Catalyst, which is part of an NIH-funded Center for Translational Research, which is trying to basically move, innovations at the bench level, at the scientist bench, to the bedside. Right? There's a valley of death between what gets discovered in the benches of scientists to what gets actually to the patients. So the Catalyst program at the medical school is geared towards helping bridge this gap.
Crossing the chasm
Exactly.
for medical innovation.
Exactly. And this is that major issue because there's all this great research being done, getting lots of big data, but nobody analyzed it, nobody that should transform it into a useful solution that can actually be provided for treatments or for patients. And so we did this study where we were basically in the end trying to discover an immunomics problem in the immune system of people by looking at genetic data. And we wanted to basically look at mutations and predict the initial sequence and the structure for the mutations along the way. It's called edit distance, to be technical. We ran a challenge on TopCoder where we basically had about 1 million sequences, and we wanted competitors to be able to write code that would basically minimize the edit distance and predict the original mutation.
To be clear, there was already an algorithm.
There's already an algorithm that exists. Yeah, so the NIH
so we're trying to optimize this.
Exactly right, and the NIH has built up an algorithm called Megablast and so on that try to solve this problem. The researcher we had that we worked with, he also had done his own research for about a year. PhD trained from Oxford, really smart guy, built his own algorithm as well. So we had 2 benchmarks available. And we said to the TopCoder community, well, we've got this problem. Can you solve it as well? And we want you to, accurately come up with the right distance at a distance that we care about. So improve the accuracy, but also do it really fast. And we wanted it done in a way so that you could actually process this data on a laptop computer instead of a cluster, basically. So we ran the challenge again. It was a 2-week-long challenge, 10 days or 2 weeks, I forget now. I think we had about 600 people register, about 122 people actually compete. We received 600 code submissions over this time period, and basically the top 30 submissions were an order, I think 1,000 times better than the gold standard from the NIH, and 100 times better than what the researcher had done. So the accuracy was better than what the gold standard algorithms were doing, but what was really phenomenal was the processing time. We basically went down to less than a minute.